using the forces method in the form of three-moment equation to determine the forces acting in continuous beams. This is a lesson and article number 2.11 from the book Mechanical Systems Calculations of the Marine Facilities. Example of continuous beam. Actually, continuous beam is the beam supported by more than two simple supporting links. So here on the sample, on the draft 2.11.1, we have zero link, first link, etc. Link number I plus 1, etc. Link by supporting link by n number, etc. Usually we start the numbering of the links from the left to right, and it can be 0. The first one link and next one is 1, and the span between links correspond to the right one number of supporting links. So this is the first supporting link. So the span is L of the length L number 1. Okay. This is link of number Y, so I, so the length is number I here. This continuous beam is statically indefinable to the degree of static indefinability. We can find by the formula for the continuous beam as number of the supporting links. Here we have 1, 2, etc. Minus 3. So how to find the support reactions of this continuous beam, and how to make diagrams of the bending moment and shearing forces of the supporting links. We can use a force method, and we can use the equation of so-called three-moment equation. Three-moment equation physical concept is that we substitute the assigned continuous beam by the set of the statically definable beams. To do that, we put the simple hinges to the connections of spans of the continuous beam at each of the supporting link. So we have continuous beam, and we put here the hinge. The hinge between two span of the supporting links is span number I. And we consider the load on the continuous beam consisting of the external load assigned to the continuous beam and the load on behalf of the fictitious moments. So we assume that we can substitute the action of the adjacent spans on each one, the left one span and the right one, by the substitute of the adjacent spans by the moments, bending moments acting on behalf of this adjacent span, the right one on the left one. So for definite one draft, as indicated on the picture 2.11.2, we see that we can do the three-moment equation of the force method of decision of the statically indefinable mechanical systems, like beams on the many links more than 2. We can define the correspondence of the deformation in the hinges. We connected when we develop the main system. Main system is the statically definable system, which loaded by the same load as assigned scientifically indefinable. the statically definable system is the assigned continuous beam, but with the hinges on each supporting link for the assigned system. And considering, for example, the supporting link number Y, we put the hinge here. For the previous one, supporting link, we put the hinge as well in the continuous beam for the right one to the number Y. On number I, we put another one hinge. And we consider three moments. Moment of the communicated from the right one to the left and to the left one to right spans to each other. The moment is of the opposite direction but of the same magnitude my. This is a fictitious moments. We assume that they are, and we have to find these moments. We consider the external load, but this load external acts only on the definite one span and do not communicate to the load itself, don't communicate to other span, to the adjacent. But to the adjacent, we have just only distribution of the moments in the installed hinges at the supporting links to do the statically definable main system of the assigned statically indefinable system, statically indefinable system of the continuous beam. So the three-moment equation is that product of moment is the moment is subject for determination by this equation. So this unknown variable on the left one, the moment on from the left one span number y acting in the hinge moment, hinge number I minus one, product by the length of the span number I, Li, plus product 2 by moment in the hinge number I, product by brackets of total of two lengths. So the left one is the right one span in the definite one. Left one and the right one span lenses for the definite supporting link I and this hinge installed for the main system statically definable corresponded to the statically indefinable assigned system. Plus product of the moment on the right one hinge added into the mechanical system to do it statically definable from the statically definable, but we substitute the action of the all rights load and the all rights spans of the continuous beam by the moment m y plus 1. Product of the moment mi plus 1 by the length of the span length number I plus 1. This is equal to product minus 6 by R F mean that the index F mean that indicator is we are talking about the fictitious support reaction. We assume that like fictitious support reaction on the whites, this one support, and it consists of two summons. One sum on the left one B fictitious Y plus A fictitious Y plus 1. B from this one left one span, A from the right one span. This is fictitious support reactions. Reaction to the total is a support reaction fictitious on the white on the I number support link equal to the sum of reactions of single span beams located to the left and to the right of the I's support from load distributed according to the patterns of the bending moment. So we consider only action of the external load to the definite one span separated by the hinge assumed or to make a statically definable system of the assigned statically indefinable. And we have concentrated load F and distributed load Q. These two laws effects only on the span number I and number I plus 1, correspondingly to force concentrated F and the distributed force Q. We can determine the reactions of in the supporting links for this just only one, considering separately each of the spans supported by the links with the hinges. And we have the diagrams of the bending moments of this each span considering separately with not action of the other spans or the right one span considered separately. This is the bending moment diagram of the triangle shape, and this one is parabolic shape, curvilinear diagram of parabolic shape due to the directed the convex of the parabolic shape directed towards the direction of the force, and this is concentrated force, and this triangle shape, the vertex here directed in the same in the projection communication directed downwards, exactly as the force directed downwards. So we have the diagrams, and we have the main system corresponding the assigned statically definable system. Main system is scientifically definable. The support reactions when loading single span beams, typical options are shown in the diagrams on drafts 2.11.3, 2.11.4, 2.11.5, and 2.11.6. So this is summons in the fictitious support reactions, summons B fictitious and A fictitious we can find for the typical options of the separate beams. As for the beam indicated on the loaded by just only one concentrated force on the, indicated on the draft 2.11.3, we have two formulas to determine the summons AF and BF by the corresponding formulas, considering the point of the application and the distance between the hinge and the point of application of force U and Y, and the force itself and the total span L, the square degree. So using this formula, we can find for definite one load, we can find the factor, the summand AF. It could be for definite one if the left one will be of the same mechanical span as the span supported just only by two supporting links. As well, we can find the B if the left one would be like all this corresponding this scheme of the simple span and supported on the hinges, on the sliding hinge on the right, on the fixed hinge on the left, and as well we can find the summand BF. And on the draft 2.11.4, if we have the loaded two forces concentrated, we can use these formulas to find this symmetric loading of two forces from the left and from the right hinge at the same distance located the point of the application of force. We can find as well the summands required to find this fictitious support reaction for the definite one considered supporting link and hinge point. If we have continuous load, we can use these two formulas, option of single span beam on the diagram. indicated on the draft 2.11.5, and we have these two formulas if we have distributed load, but not for all lengths of the span, single span, but this is for just only distribution of the load due to the half of the span. So this is about that we have typical options which can be used to determine the fictitious support reaction on definite one support of the continuous beam when we do from the continuous beam statically indefinable, when we do the static of it, the statically definable mechanical system of the single span beams, single span from continuous beam, we do a single span beam. Yes, and the exercise is indicated in the draft 2.11.7. We have the continuous beam. Continuous beam supported in at the two ends, and this 1, 2, 3 we have as well. This is a 3 intermediate supporting links here, and we have to determine the diagrams of bending moments and shearing forces using the force approach and using the equations of trim moment. Transform the diagram of continuous beam to main system. Well, main system is a statically definable system consistent of the single span beams. One applies a moment and transverse force on the support instead of the distributed load acting on the console. So we have the console here, and the console do not have the support on the right end. So we first can substitute the action of the console by the moment M4. M4 is not difficult to find. M4 is equal to minus 3 minus product 3 by 2 in square degree divided by 2 is equal minus 6, and we can find the shearing force acting on acting here on behalf of the acting on the 1, 2, 3, 4 on fifth link. Instead of the console action of the beam, we substitute by the moment and by the shearing force. Shearing force is the area of this diagram for the console. For the length of 2 meters, we have 3 kilonewtons. So together we have the force, shearing force at the end, like 6 kilonewton. The general form of three moment equations for remained main system. We substitute the supporting links, besides only two ones on the left one and the right one. We substitute these 3 by the hinges installed in the points of the connection of the supporting links. And we have, in a general approach, 3 mathematical equations of for each intermediate support. For the first one, we have the 3 moment equation, like the product M0 by L1 plus product 2 by M1 on the first hinge, and supporting link by brackets in brackets is sum of lengths of lengths L1 and L2 plus product moment M2 acting on the right end of the second span by length of the second span equal to minus 6 and fictitious load on the first one link. And this is for the first one. For the second one, we have the same, considering the adjacent two lengths of the left one and the right one spans of the main system. Differs with the assigned system that in the supporting links of the assigned system. Here here in 3 supporting links intermediate, besides of the 2 supporting links at the ends. For this 3 intermediate, we put the hinges and we separated this continuous beam by the set of 1, 2, 3 by 4 simple spans, which do not, which are not assumed not to be parts of the continuous beam. And for the separate single span, we have to find bending moment diagrams. We do not have the load on the span, external load on the span number 2. So we have the hinge number 2, support links number 2. So left one step, we have the span number 2, left from the support 2. And on the span 1 to the left from the supporting link 1 and the hinge 1, we have the bending moment diagram of the triangle shape. And we can find as well the magnitudes of the diagram. But first of all, I would like to explain how it looks like on the main system. On the span number 3 to the left from the hinge number 3 and supporting link number 3, we have the one triangle, the superposition of 2 bending moment diagrams, one triangle diagram, and one as a segment, very small segment from the diagram of the distributed load here, of the parabolic shape. So it is not definitely the geometric triangle, but it's a triangle with some the adjustment of the segment of action of distributed load causes the parabolic shape of the diagram to the diagram of the concentrated force, which is of the triangle shape. To the right, we have distributed load, evenly distributed load, and we have the parabolic shape of a curvilinear diagram of the bending moment. So it's just only we need to find the magnitudes of these vertices of the triangle diagram, or this parabolic diagram, etc. With this one triangle diagram with a parabolic segment. So the vertices we have that the length. First, easy to say that about the length. The length of the first span is 3 plus 2 is equal to 5 meters. The length of the first span, the vertex is 12 kilonewton by meter. It's 12 kilonewton. We can, if we do consider the equations of balance of this one single span, consider rotation around the point 1 and point 0, we can find the support reaction for this single one span. And the left one reaction with the arm of 3 meters give us a magnitude of the moment in the vertex of the triangle diagram of the bending moments here. And besides of that, we can find the location of the, it's very important for the determination of the fictitious load here, that it is proportional to the product of the area of the diagram of bending moment. This is area of diagram bending moment for the span number I. And this is A is the extent of the point of area of diagram of bending moment from the left support in the span number I, extent A, and divided by Li. Li is the total span length of number I. So AI is the extent from left support of I span to definite one center of the area of the bending moment diagram. And having that the extent is known the rule if you have the triangle, how to find the location of the center of the area of triangle from the left, for example, A1. So we have to do the total of coordinates of each vertices of the triangle. The first coordinate, we coming from left to right. The first is 0. The second coordinate is 3. The third coordinate is 5. 5 is 3 plus 2. So when we have a total of these 3 coordinates, 0, 3, and 5, we can find total and divide by 3. And divide, have a total and divide by 3. And we have that distance from the left point of the triangle shape bending moment diagram is 2.67 meter. If a total span of the total length of the first span is 5 meter. From the right one side, we can just only take a difference 5 minus 2.67, and we can find it from the right one end of the span, from the right one support of the single span. We can just find 5 minus 2.67. I will have 2.63, but the same way as we did the previous one, we can find that B is coming from right to left, is we determine as distance B from the right one to left, distance to the point of from the right one support of the single support beam. To the left we have by the B, and from left to right we have first A. So 0, 2, 0, 2, the point of the application of the force is 2 meters to left from the hinge and the simple supporting links number 1. And next is 5. 2 plus 3 is 5, referring from the hinge number 1. So as well, we can find that the B, the distance of to the point of area of the triangle shape bending moment diagram is 2.23 meters starting from right to left. And after the substitute into the of got magnitudes to the formulas of the summands of the R, F, I, this one, I plus 1, and B, F, I, using these formulas after the substitute of the magnitudes got, we have the area of the diagram omega I, omega I we have as the area of the triangle is 1, 2, the half product of half by the length of the triangle by its edge. So, and we can substitute this all into the formula of summand of the fictitious load R, and we can find that is 14 kilonewton by meter in square degree. This is dimension kilonewton by square degree of the summand. The same we can find that B for the first single span. And we have that it is, after the substitute of magnitudes, we have that it is 16 kilonewton by square meter. Next, we consider second span. Due to the bending moment diagram for the second span is 0, we have no loads on the second span. If we consider the second span as a single span taken separately of the continuous beam, separated from other spans by the hinges at the ends of the second span. So we have that the area of the bending moment diagram on the second span is 0, and exactly the summands of the fictitious loads at the second hinge and second supporting link is 0, 2. So yeah, we have 0 bending moment diagram on the second span. Next one, third span. Third span a little bit more complex because we have to consider not only the triangle part of the bending moment diagram, but as well for the left half of the third span, we have to consider the segment of the parabolic shape due to the action of the distributed external load. Considering just only this one, so the span, single span with not the continuous beam for the whole span, just only this one, separated from other spans by the hinges at the ends of the third span. So we can find the area or the triangle shape, we indicated it by the stroke. So the area of the embedded moment diagram of triangle shape on third span is omega 3 stroke. So which is 1/2 of length of the third span product by the magnitude of the bending moment diagram caused by the concentrated force, this one. And this we can find this bending moment magnitude in the middle of the third span by developing of the equations considering action of the concentrated force on the span, finding the support reactions, and after that we can find the triangle shape of the diagram of the bending moment caused by the force concentrated on third span, and having the magnitude and the length of the triangle diagram, we can find its area omega 3 stroke. It is 67.5. So the point of A3 stroke and B3 stroke is distances from each ends of the left one and the right one ends of the single span number 3. We indicated as A3 stroke, B3 stroke due to the symmetry of the action of concentrated force acted applied to the middle of the third span. We can find that the distances between the hinges of ends, hinges at the ends of third span are equal 3, and using the formulas for the summands of the fictitious load B fictitious y and A fictitious y plus 1, we can find that the A fictitious F3 stroke equal to B fictitious F3 stroke is equal to 33.75 kilonewton, 33.75 kilonewton product by square meter. Next one, we consider the parabolic segment due to the caused by the distributed load on left half of third span of the assigned continuous beam, and considered a single span beam between second and third supports, separated from other beams by the hinges installed on the supports. And we can find that the area omega 3 two strokes of this one part of this one segment of the bending moment diagram caused by the distributed load area is 2, 3. Is only the part of 2 divided by 3 part is a grade, and the product by the length of action of the distributed load on the third span, and product by the magnitude of the force of the bending moment caused only but by the distributed load on the span of 3. This we can find these magnitudes considering the third single span separately and loaded only by the distributed load, and considering the balance equations and finding that support reactions, and after that we can find the segment magnitude H3 two strokes, this very small segment of the magnitude, and we can find each area like product of the grade 2 divided by 3 product by length and by magnitude of the bending moment diagram caused by distributed load in the left part of the single span number 3. So we have this as 4.5 kilonewton by square meter. Just it's very useful in the structural mechanics that when you have to find the area of the parabolic segment of the diagram, its area usually is the product of the grade 2 divided to 3, and the product to the size of the span and the magnitude of this maximal magnitude of the diagram in the center of it. So if we are talking about the triangle shape of the diagram, the factor is just a half. So the grade 1 by 2. Here the grade is 2 by 3 for the parabolic shape of the bending moment diagram. And after that, we can find A3 two strokes and B3 two strokes, the distance from the right one and from the left one, hinges of the single span number 3 to the center of area of the bending moment diagram caused by distributed load, as we consider the distributed load for this left one half of the span number 3. We see that the center of the action of the distributed load from the left is 1.5 meter, from right is 3 plus 1.5, that's equal to 4.5 meter. And we can substitute this all into the formulas to determine the sums of the fictitious support action, a B fictitious and A fictitious for span number 3. We can have that as it is for parabolic segment as 3.375, and B is after substitute of the magnitudes of the areas of the bending moment diagram of the external load to the single span number 3, considered separately of other continuous beam. And B fictitious two strokes is 1.125 kilonewton by square meter. And exactly, and we can do that if we have to find the total of the factors are fictitious equal B fictitious for the action of the concentrated force on the 13 span. So we indicate by the strokes, and R fictitious and B fictitious two strokes we can use together in the equations when we determine the fictitious load of the right side of the 3-moment equation. And then we can consider the 4 single span is 4 single span loaded by the distributed load, so it is the segment of the parabola shape. So we find that as the maximal we can find here, the magnitude and the maximal magnitude of the bending moment diagram is 6 kilonewton by meter. It's easy to find as we can consider the formula of the bending moments for distributed force. L is equal, it could be any, maybe we can consider like this one kind of the load, this one kind of the load. This we used for determination of the fictitious loads as well. If we don't want to consider the balance equations and to determine the bending moment diagrams ourselves, so we sometimes this is usual cases, and we can use previously have decisions for this kind of the loading of the single span. Due to the force span is symmetric, so A4 and B4 is distances from the left hinge to the center of the area of the bending moment diagram equal to distance from the right hinge of force span to the center of the bending moment diagram equal 2 meters because the total length of force span is 4 meters. So after the substitute in the summons of the fictitious load RF, considering the formulas indicated before, here we can find the summons of fictitious in the force span AF4 and BF4 as H kilonewton by square meter. After that, we can find the fictitious, so just the assumed or imaginary external load indicators on the right side of the three-moment equation. We use a formula indicated before. This one formula we use, and we can determine that assumed or fictitious external load indicator for the first hinge installed instead to do the separate of the first and second spans of the continuous beam, making the main system of the continuous beam statically definable, and installing the hinge we do the statically definable main system corresponded the continuous beam. So we can find that RF1 is 16, RF2 is due to we have two segments, and the triangular segment and parabolic segment for the third span we use together to find the summand RF3 in the formula, and for the for third span we consider second, the right one is third, the left one is second, but load external to the second span is 0. So we have this one, RF2, the assumed or fictitious external load. And RF3 we have as well by this formula. This one consists of two segments for triangle bending moment concentrated force acting on span number 3, and this is the factor of the action of the distributed force for half of single span number 3 plus H. H we got here as for the force span, single span, and we have RF3 is equal to 42.875 kilonewton by square meter. Based on initial data and when creating the main system, the following supporting points are determined. So we have the left one magnitude of the moment on the left one hinge of the continuous beam 0, and on the right one hinge we have -6 due to we had the console part of the right one hinge, console part of 2-meter console part rotating clockwise. So this minus M4 we got originally -6 kilonewton by meter moment. We are coming to find the moments at the hinges, which corresponds to the rule of equality for each hinge of action of the left one and the right one hinge. Left one and right one parts of the mechanical system acting transmitted through definite one hinge to the another part of the mechanical system. So we have to find 0 and 6 moments we have. We need to have magnitudes of 4 second, third bending moments in the hinges of the main system. So we have for 3 hinges for 3 intermediate supporting links. We have 3 equations and 3 unknown magnitudes to find. From the first one, we have, for example, derived number M1 in the system of the equations. Derive a moment in the on the first hinge by the moment on the second hinge. On the last one, we can derive. Maybe it's more comfortable to derive the second moment. Use by the first moment, and from the last one, we can derive second moment by the third moment. And after the substitute, no, this is exactly more comfortable to find the moment on the first hinge from the first equation, and derive the third moment from the last equation, and substitute it into the second equation together. And we next find that the support moments are found. First, we can find, for example, from the second equation that M2 is equal to minus 6.8 kilonewton by meter. After that, we can substitute it from the first equation, and we can find that M1 is minus 3 kilonewton by meter. And now for the by using the third equation for the supporting links, and instead the assumed hinge there making the main system, we can find that the moment in this have to be equal due physically to do the communication. So all single spans as it is in the continuous beam, we have the third moment equal to minus 9.6 kilonewton by meter. And we can make the diagram for the single span of moments of the fictitious load, which gives us the continuous distribution of moments along the whole continuous beam. So if the moments in the hinges will be the magnitudes of this one, which was 0 exactly, this is hinge, not a assigned hinge, but it was from the first of the assigned system, not assumed hinge. After other hinges was assumed, but if we have the magnitude of any moments here for the first one, supporting 3.1, the second one supporting 6.8. You got from the mathematical equations of three moments. And from the for the first, for the second, for the third, we have 9.6, and the right one is the action of the console distributed load on the right one span with not support here. And we have two diagrams of bending moments. This we have to consider this action together, and when we in the projection communication do summarize these two diagrams for determining diagrams of bending moments, we can have the diagram of the bending moments for the continuous beam. This diagram of bending moments are the result of summarizing of these two diagrams in the projection communication. So here we have 6 and 8, here we have 3 and 1, here we have 12 minus 1, 86, minus 1, 86 is 10.14. Here we have 14.29 as in the middle we have H 0.21, but for the single span number 3 we have here the magnitude H3 stroke. H3 stroke is this two stroke. H stroke is 22.5. So 22.5 minus 821 we have the 14.29. Here we have 9.6, and here we consider together two magnitudes of 781 of the imaginary support moments of the of the fictitious of the decision of the bending moments, we have 7.81, and for single span we have 6, and we put it together. On the right we have 6, and we have the part of the bending moment diagram for the console segment. As for the distributed load, it is the parabolic together with the triangle. Triangle is due to the bending moment on the support, and the parabolic together, it gives us like this parabolic and triangle segment. And the second, what we have to do, we need to make a diagram of the shearing forces. Usually, it's more comfortable consider the derivative dependence of the bending moment diagram and the shearing forces. So bending moment diagram is an integral function of the shearing forces diagram, and if we did first the diagram of the bending moments, we can start to determine the diagram of shearing forces from right to left. So for this segment from 0 to 6, the derivative is the increased function is starting 0 to 6. 0 to 6. This is because we consider the this one is derivative to this one. So the area of 6 by the area of this triangle correspond the magnitude of this bending moment. The console extent is 2 meters. The magnitude of shearing force 6 meters. This just had to verify is it correct or not. 6 meters. So the area of triangles, the half of the product of half of the magnitude by this one leg, half of the is triangle area, and 2 meter half, and 1 meter, and the magnitude 6, 0.5 product by 6 and by 2 is 6. This way, after that we have the second one part of span, and the negative magnitudes of the distributed load, and this corresponds the reduce of the bending moment diagram from 6 to 1.81. The minimal of the bending moment diagram corresponds to 0 of the derivative. After that, we have a positive magnitudes of the shearing forces, because the bending moments increases again to 9.6. After that, the bending moments diagram reduces from plus 9.6 to minus 14.29. The signs of the bending moment diagram is relative. If we usually starting right to left, we can consider as rotating the counterclockwise positive, clockwise negative. So for the 14.29 minus 9.6, we can find this size together, two sizes of these two legs, and we can divide for the extent to the center of this span number 3, and the length is 3 meters from the flat hinge to point of application of the force, concentrated force on the span number 3. If we this difference of these two magnitudes divides by 3 meters, we can find minus 7.97. This is magnitude of the evenly distributed shearing force. This part consists of two segments. Actually, we could have like a magnitude of 4.03 and evenly distributed, but if not, the distributed force to this definite one span. So we have distributed force and we have a concentrated one. So the concentrated caused the step in the diagram of the shearing forces, but the inclined part of the diagram of shearing forces corresponds the action of the distributed load. And we have this very positive because magnitude from minus 14.29 increased to 6.8 increased with acceleration. So the inclination increases as well of the tangent to this function. So inclination corresponds to the magnitude of the shearing forces diagram. So for the span number 2, we have the shearing force diagram with a little bit minus 0.74, and we can see that the bending moment diagram slightly reduced from 6.8 to 3.1. This is because we have other support reactions at the ends. At the ends of the single span number 2 of the continuous beam. And here we have the reduce due to this minus we have on the shearing force diagram. This minus corresponds to tangent of the angle of the inclination of this part of the diagram of the bending moment. So from the geometric point of view, this area of the diagram of shearing force corresponds to 10.14 plus 3.1, the total magnitude of these two at these two ends of this part of the force span. And after that, the diagram of bending moment linearly increases to 0 from minus 10.14. It corresponds the positive derivative, which is 10^14, and the magnitude of this evenly distributed diagram of the shearing forces is 10^14 if divide by the length of this part 3 meters after the starting right to left, after the point of action of this concentrated force 10 kilonewton. This one part is the distance we divide, and we divide this 10.14 to 3 meter distance between this point of application of the concentrated force to the left one hinge, and the division of magnitude to the length of this part of the span number 1 is result 3.28. So we have the diagrams of the bending moment shearing forces assigned. Besides that, we can exactly find the support reactions of the hinges, intermediate hinges here. The support reaction is for the first hinge 6.5 plus. Each step corresponds to the support reaction magnitude. This support reaction is 11.1. This is 7.97 plus 6.91 directed downwards here directed downwards, and here support action directed downwards, and the magnitude is 10.01 plus 0.74, and we can find like 10.75. This is a support reaction directed downwards, as we have here the step downwards. And here is 6.62, the support direction minus 0.74, the support direction directed downwards as the size of the step. And it a little bit less than 6, like 5 and some else. And here we have the support, excuse me, all these support reactions turned upward. Excuse me, I mistaken. Yes, all this, and the left one is directed upward. All support reactions directed upward on the external load. But the magnitudes of the support reaction we determined as well correctly as a magnitude of the each step for each of the supporting links, intermediate and right one and the left one. So, and the questions and comments. The concept of continuous beam, the degree of static indefinability, concept of continuous beam. The continuous beam is the beam with more than two supports at the ends. The degree of static indefinability for the continuous beam is number of the supports minus 3. The number of the simple supports minus 3 depends exactly on the kind of the support. The basic system when calculating the continuous beam. Basic system when calculating the continuous beam by the force approach and using the three-moment equations, the basic system is the single system of the set of the single span did from the continuous beam by installation of each at each of the supporting links of the hinge, separating the continuous beam into the single into the set of the single span beams, using the forces method in the form of three-moment equation, the physical concept of three-moment balance. Physical concept is that the action of each of the adjacent single spans in the main system of the continuous beam is substituted by the moments which have to be equivalent to the left one and right one adjacent span in each of the supporting links, substituted by the hinges instead to separate the continuous beam into the independent single span beams between each of the supports, each couple of the supports. The fictitious support reaction on the support equality to the sum of reactions of single span beams located to the left and the right of the support from the load distributed according to the pattern of bending moments to find the fictitious support reaction R, F, I for each one number I support. We consider the diagrams of bending moments for each of span to the left and to the right of support and hinge installed to do the single span of the continuous beam. And we consider the diagrams of bending moments, assuming this like this span are independent on the left and right of all adjacent span other of the continuous beam. Typical examples of single span beams used to find the support sections is formulas if you don't want to do the calculations of each of single span or main system from the continuous beam. So for the single span, we have the previously done the formulas for the typical options of the loading of the single span, and we can use these formulas to determine the summands of the fictitious summands BF and DF, or the fictitious reaction required for the right side of the mathematical equation of the moment approach. Moment equation for each independent intermediate support. Yeah, we had the formula calculations of fictitious, the assumed or imaginary reactions along spans of a continuous beam. Now we can do all the decision for each of single span did of the continuous beam. Considering the balance equation for each span separate of other span, or to find the fictitious or assumed reactions, or we can use the typical formulas for the typical cases of the loading of the single spans. Finding of fictitious imaginary external load. It is a total of two summands. R we denote as R fictitious with indicator F. It is the result of total of two summands R fictitious and B fictitious of the action of load of the span located to the left and to the right of the considered supporting link when we, because we do develop the three-moment equation for each of the intermediate supporting link. So to do that, we consider to the left and to the right the spans and considering the diagrams of the bending moments to find the fictitious or imaginary external load. Finding support moments using three-moment equation, we can decide the three-moment equation system to find the support moments. Any approach to decide the support equations. It can be available in the Excel approaches to decide the linear system of mathematical equation, or matcat system we can use to find the to use a three-moment to find the support reactions. Determine diagrams of the bending moments by summing the diagram of moments from span load and the diagram of the support moments. Yes, it did. It is doing by the projective communication. So we consider two diagrams. One of the bending moments from span load, and another one a diagram of the support moments found by decision of the three-moment equations. And together they gives us the bending moment diagram, find the diagram of transverse or shear forces by differentiation, the diagram of the bending moments. Yes, this is one of two approaches how to find the diagram of the shearing forces, because they are with the diagram of the bending moments in the derivative interdependence, the diagram of the shearing forces, the function of the shearing forces is a derivative of the function of the bending moments, and the diagram of bending moments is the integral function of the shearing forces. So we can use that property, differential interdependence, to determine the diagram, having one as, for example, the diagram of bending moments first, after the use of this is usual after the use for decision of three-moment equations of the force method to decide the continuous beam statically indefinable. In this case, first we have the bending moments magnitudes, and we have the diagram of bending moments, and we can use it to find the derivative diagram. And this will be the diagram of the shearing forces. Thank you.